windows and doors really give architects a hard time. I think it really has to do with, honestly, I think what trips a lot of us up is there's just so many different profiles. Like if you look at a section, or I mean, anyway, there's just so many different profiles of different kinds of windows and doors. And it seems like a bunch of lines and we don't know what the actual profiles do. So we're like, well, if I don't even understand how this works, how am I possibly going to design the window to wall interface? And the good news is you don't actually really have to fully understand how the window system or the door system works in order to detail the window to wall interface properly. You need to know a few things, but you don't need to know the ins and outs of every single profile, which is good because most of the times when you're doing your detailing, you start doing your detailing in professional practice, you haven't bought the client hasn't decided what kind of windows and doors they're actually going to buy. So you have to be at least a little bit generic with this stuff. And the good news is that the approaches I'm going to talk to you about today actually lend itself very well to that kind of generic approach. It's really pretty easy. I mean, easy to move things around on a real job. You can move a sealant joint around in pretty much any time up to the actual installation. But getting something added to the drawings, as many of you know, practicing at firms, after the bid set has been produced is very difficult. It's costly, it's not fun, you get a change order, you feel like you've screwed up personally, and people act otherwise uncharitably toward architects when they try to add something later. So moving stuff is fine, adding stuff is difficult. So we're going to try to get it so that you know how to get everything on the page in approximately the right order. You can move stuff around later to accommodate a particular system. But I'm going to try to give you a general approach that applies pretty universally to almost any kind of window or door. So with that, before we talk about actual windows and doors, we need to, let's make this bigger here, set the stage a little bit. So here's what I'm going to talk to you guys about. I'm going to give you a general approach to sealing the window or the door, like the philosophical foundation to this stuff. We're going to talk about stuff you need to know first. So it's going to be a list of things that you're going to, not a long list, but things that you're going to need to figure out before you start detailing. And don't worry, it's an actual obtainable stuff you can figure out. And then we're going to talk about some typical configurations. We're not going to be able to talk about everything on this list. This, by the way, is straight from the course that I teach, the more formal course. But we can't get to all of it in 45 minutes, but we can get to at least the first couple, and then maybe we can talk about some specifics in the Q&A if you have specific questions that we don't cover. And then we're going to talk about frequently asked questions about these typical configurations. Oh, and one thing before we go into this is, remember I told you just a moment ago about how the profile of these window and door systems really trips a lot of architects up. Sometimes it can feel like you're the only one who doesn't understand what the ins and outs of that particular system. And I will tell you that it is my job to review drawing sets. I do it all the time, and I review drawing sets from lots and lots of different architectural firms. I've seen a lot of drawing sets from a lot of different firms, and approximately 50% of the drawings that I review, architects will label the window profile incorrectly. They'll call it a curtain wall when it's really a storefront, or they'll call it a storefront when it's really a curtain wall. And I'm telling you this not to say that you should get it wrong, but I'm telling you that pretty much, like, there's a lot of confusion in it. And a lot of people end up seeing these and they've gotten them wrong. And by the way, the buildings get built and it's just fine. Anyway, so you're not the only one who doesn't understand this stuff, I promise you. And I'm going to make it so that you don't have to understand everything to do a good job anyway. Okay, so let's see. Okay, so a window has to do all the things that a wall has to do, and you have to be able to see through it or walk through it, right? In the case of a door. The windows and doors need to control water, they need to control air, they need to control heat, and they need to control water vapor. Same thing as the wall. And what our task is to connect the control layers at the wall to the control layers at the window in a way that's, you know, safe, durable, efficient, that kind of stuff. So I want to start with a theoretical, like just a thought experiment. So suppose you were to hold a cup and you were to, you know, I've got a cup actually, but there's tea in it, so I'm not going to do this, but turn your cup horizontally so that it's facing the wind. And you're going to allow wind to blow into that cup. And then suppose that it's also raining when you do this. So I want you to think about what is going on inside the cup. If you've got a cup that's facing the wind, the cup is going to fill up with air, right? The wind is going to blow air into the cup, and then the cup will be full of air. And once it's full, no more air can get into the cup. So you're going to have a positive. I wish you could see my mouse. I'm going to pause for a second here. Hold on. If I do this, you can see like my whole screen and my notes and stuff, but can I get a thumbs up if you can see this sufficiently?
We can see, yeah, we can see your mouse.
Okay, so I'm going to do this. You're going to see some of my my notes here, which maybe get interesting. I don't know, but I think it's more valuable to see the mouse. So okay, so we're going to go back here. So the cup is full with air. We get a little bit of water in our cup, but it's open. It's like totally open. So any water that gets in drains out. But the important thing to note here is that this part of the cup that's open to the wind is going to have a positive pressure. And behind the cup, there's going to be a negative pressure. So there's a wind pressure across this vertical divider. So we've got a positive pressure on one side and a negative pressure on the other side. It's pretty simple, right? Like this makes intuitive sense to most of you, I hope. So we start there. And now let's take our same cup and see if I can do this. There we go. Let's add a baffle to the cup. So we're going to add a baffle that doesn't cover the full opening of the cup, but it covers it partially. And the baffle will deflect raindrops and it'll reduce how much water gets into the cup, but it's still open and it still allows that cup to become pressurized from the wind. So we've got basically our same scenario. We just don't have as much water coming into the cup from momentum. And if we do get a little water in the cup, it can obviously very easily drain out. But again, note this pressure difference here. Positive pressure inside the cup, negative pressure on the outside. So positive pressure on the windward side, negative pressure on the leeward side. So now if we take this same concept and look at a window. So this is a generic window profile. And instead of a cup, we've got what we're calling a pressure chamber right here. And it's open to air and it lets water out and air in. And so just like our cup, we're going to have a positive pressure in the chamber and a negative pressure in our building. And so the pressure drop is going to occur at that same sort of divider here, the rearmost divider. And what this creates is kind of a neat system in that our exterior seal from our window here, it will see water, but it doesn't see any pressure. The pressure here is the same as the pressure here. Now there'll be, pressure from gravity a little bit here, but it's not seeing wind pressure. Now here, we'll see a pressure drop between this interior seal and the chamber, but we won't see any water because of where it's located, which is kind of genius, right? So the effect of wind-driven rain is essentially nil on our inner seal. Or we don't, because we get pressure here, but no water. We get water here, but no pressure. It's awesome. Now, let's look at a window to wall interface. This is greatly simplified. We're gonna get into some configurations later, but I wanted you to appreciate the concept. So now we've got a different pressure chamber. We've got a pressure chamber here. And we've got an interior backer rod and sealant joint and an exterior backer rod and sealant joint. And we've got a weep in it. picture a small tube, like a straw. So that weep will allow water out, but it'll also allow air in. So we'll get a wind and it'll blow against our facade and it'll fill up this chamber. So this will become positively pressurized and it'll be the same pressure as the outside. This will be under a negative pressure comparatively. So this inner seal won't see water, but it will see pressure. And this outer seal will see water, but no pressure, which is really kind of cool. It's even cooler if you consider that any seal that's outboard gets exposed to a lot more loads than our inner seals. So our outer seals see a lot of UV, they see impact damage, they see birds pecking at it. You know, it gets abused. These seals get abused. These seals are pretty well protected.
You got a question.
Great.
What is the benefit of bringing the pressure inside the system?
It's exactly what I'm describing. It's that when you get this chamber that gets to be the same pressure as the outside, it's just like the baffle with the cup. We're allowing pressure to be in here so that we're negating wind-driven rain. Once our cup is full, it can't get any more full, right? You can't, if you have a cup of water and now it's vertical, let's say, and actually we pour tea into the cup. Once it's full of my tea, it can hold no more tea than it already holds. And the same is true if we rotate it horizontally and it fills up with air. Once it's filled with air, it can't fill up with more air, which means that a baffle is all we need to deflect the rain. We have no pressure driving rain into that chamber. So we always want the pressure in the chamber to approximately match the pressure outside. And this is actually similar to what you might have heard people describe pressure equalized rain screens. It's not really pressure equalized, it's more pressure moderated because the pressure in here doesn't 100% track the pressure outside in real time. There's a little bit of a lag sometimes. Buildings are complicated, the wind isn't completely even all of the time. But what that does is it means that it counteracts the effects of wind-driven rain. And this is how window systems and some facade systems work on the tallest skyscrapers that we build, right? The wind pressures are enormous on those buildings. This is exactly how these systems work. These those curtain wall systems work the same way. Now, the kind of secret with this is that pressure equalized, or what is called pressure equalized, but never say that. You'll hear that. Don't say that. Say pressure moderated. It's a little bit more modest. These pressure moderated systems, they only work when the space that's becoming pressurized is small. If the space is too big, if that joint in question is enormous, like it's an entire facade, like a brick facade with a 2-inch cavity for 2 stories, that and the wind blows against that, and you've got some weeps and vents in the brick, that entire space is not gonna, the pressure in that space is not gonna match the pressure outside. It's too big a space for that to really occur. But if the space is small, like a joint in a window or within a window frame, the pressure will more closely track the pressure outside. So you won't get a continuous influx of water and wind. So I hope that makes sense. So the particular reason.
One more question says, because of the Bernoulli effect? Is that was a question?
Honestly, I don't know. I've heard the Bernoulli effect. Michael, you probably know it better. I don't pay attention to it. It's because of a cup. because of the way, because I'm a sailor. Like, because of why we fly. Is that Bernoulli?
Yeah, I don't remember if that's Bernoulli or Venturi.
I don't know. Venturi, maybe? Maybe it's the Venturi effect.
Basically, if there's, well, you explain
one of them.
Well.
You could tell someone it's Bernoulli and they probably won't know. So you can use it if you want. But anyway, so an additional reason this is so awesome is that these outer seals, our system works, these see a lot of abuse. This seal and this seal sees a lot of abuse. But what happens if these seals fail? Our system still works because we still create a pressure chamber. Even if this seal degrades and isn't perfect over time, it's already weeping. Doesn't matter. Now this seal and this seal needs to be thinking perfect. We need to maintain these, but these seals are a lot easier to maintain, and they don't see the same kind of exposure to UV, to birds, to I don't know, whatever else could be damaging your seals on the outside. These are much more protected, and they're easier to maintain because you can maintain them often from the interior. But this is just a very generic profile. So let's look at an actual.
You have one more question.
Yep, okay.
So this makes sense for how the wind is hitting the frame, but what the wind, rain that hits the glass? Or do the outer frame / seals?
Oh, I think I lost Tyler. But I get
Or
I lost.
I said, or do the outer frame / seals pick up the wind and rain before it reaches the glass?
Okay, great question. So the reason the glass works is because the glass itself is completely monolithic and it's perfect. So yes, so if you're looking at the glass, so I've talked about here. So the glass here is taking, and this is ostensibly a vacuum. This is taking, like if you think of it as a more monolithic material, even though there's two panes, the entire pressure drop is occurring across the glass as well. You are absolutely correct. So the pressure here will be positive, just like it is in the chamber and outside. And the pressure here will be the same. So that entire pressure drop occurs across the glass, yes. Now we're not that concerned with it because the glass can actually be, it's engineered to be monolithic. There's no joints in it. It's just a glass. But when you have glass that's in frames, they design frames exactly like this to allow kind of weeps and drains and pressure relationships. The glazing systems themselves take advantage of this pressure relationship to deal with wind-driven rain. This precisely why they're doing it. Now, this is very, very simplified. You'll look at a glazing system. Hold on, I've got a puppy here who wants to be held. Come here, see. Come here. Now she's shy. They're essentially designed in that way. You're not going to be able always to kind of parse through how they specifically work when you look at a profile, but that's generally it. And they take advantage of exactly that relationship because not everything can be monolithic like the glass. They have to have joints and things. So this is how we're dealing with joints. If we could be monolithic, if it was sort of feasible for us to have just completely monolithic materials, that lent themselves very well to being monolithic on a giant building or even a house, then we could maybe do that. But most of our building materials just don't lend themselves very well to that. We have joints everywhere.
One more, Christine.
Just take it away.
So the seal is the baffle in your analogy to keep birds, water, snow, etc. out.
Correct.
Why a seal and not a screen?
Good. Actually, I've never heard that question before, ever. I think the seal itself, because we weep it, like you could do same reason we don't have a screen, and the same reason a baffle works better than a screen here too. I mean, a screen would work okay. A baffle probably works better. It deflects more water. Also, it probably from a completely practical perspective, it is more aesthetically pleasing. I don't really know specifically why. You could use something kind of like a screen. It is true that when we use seals, these seals will fail over time, and they have to get really, when they're designed like this, they have to get really bad before the whole system fails, which is part of the genius. So theoretically, you could use something. I think it's just really about how well they reduce the load on everything behind them. But this concept should be familiar to you guys in that it's essentially the concept of the rain screen, right? A lot of times when we think of our control layers in our wall, we think of our water control layer as being the only thing. That's it. That's the thing that controls water. That's not really true. Our water management system in a wall, when it's a rain screen assembly, when it's a drained wall, I prefer using the term drained assembly, is It's the same approach. It's not just our WRB that's doing the entire job of water management. It's our WRB plus an airspace plus our cladding. And the cladding is water shedding, and the water control layer protects everything else that's moisture sensitive behind it. But these things work together. You know, it would not be appropriate to use the water control layer and have that also be our cladding. That's not how they're designed to work. And it's not an accident either. It's not, and we're gonna talk about this a little bit more as we get into this. A lot of people think of this seal as the redundant seal and this seal as the primary seal. So we do this for backup when this one fails. No, that is not the right way of looking at this. These seals together represent a system, and they are designed to work together. It's not that this only becomes valuable when this fails. They're both equally valuable right from the beginning. We're gonna reinforce these concepts in some actual windows here. Okay, hold on. But Pancake wants to say hello. Actually, she doesn't. She just wants her dinner. But okay, so this is a window sill detail, fairly simple, and a residential window sill, just to start us off. And I want you to connect what we saw here to here. Now, I probably should have flipped this. This is now the outside. This is now the inside. But what I'd like you to recognize here is we've got a little chamber. So we've got an opening that we've protected with that bright pink. It's a fluid membrane. So that's protecting the moisture sensitive. That's protecting our framing. But we've created this little chamber, and we've got a flange in our window. We'll talk about that in a minute, but it's not sealed. So water can get out at our sill and air can get in. So we can deal with that pressure relationship. And then this is our interior seal. So this is our water shedding, our zone of water shedding, and this is our waterproofing. These are our system that creates the chamber in the middle. And this is the sill though. So I just said this actually. So the outer seal is similar to the baffle. It sheds water, it protects the interior seal from impact and exposure, and it is discontinuous. Really important that it's discontinuous to permit drainage. And the system will function as designed even when this seal is imperfect, and it continues to function as this seal deteriorates over time, and it will deteriorate over time. Seals get really, it's called elephant skinned. I'm sure you've seen this on buildings. They get old and gross and not perfect anymore. The way that we're going to detail our windows doesn't depend on our outer seals being perfect all of the time. Now, the inner seal is completely continuous. It's the air seal. I said redundant. I should change that because I don't like the terminology. It receives a lot less abuse from impact and exposure, and it's more durable because of that. And it should be installed perfectly or near perfectly for the system to function as designed. We don't want to miss this seal. It's not incidental. This isn't the seal that the painter installs or the drywall contractor installs. It should be installed by the glazing contractor. I'll talk about that more later too. Quick aside, when we talk about, I sort of referenced this earlier, there are 3 different water management strategies in walls. You can have mass walls, perfect barrier walls, and drained walls. And the majority of our work in North America is here. It's in drained walls. Now, mass walls handle water by, we allow them to get wet, and then they dry out in both directions. And the reason they work is that they're not made of moisture sensitive materials, and they have a great capacity to actually hold water safely. They just physically can hold a lot of water. They're heavy, and they can safely dry in both directions. Perfect barrier walls, if you think of like the Apple Store or insulated metal panels, these walls are complete, like they are perfect barriers. So they should be detailed in a way that no water gets behind them. This is rare for us to build with this type of wall is pretty rare, mostly because the materials that lend themselves well to being detailed to be continuous are not the materials that we prefer to build with. Like you can do it with insulated metal panels and you can do it with glass, but you can't really make siding like this. You can't really make brick like this. Like it just doesn't lend itself well to this kind of perfection. Drained walls, as we are most of the time in North America, and they're kind of genius because it allows us to build out of moisture sensitive materials. We have this WRB, water resistive barrier is the code term for it. We've got a water control layer that protects all the moisture sensitive parts behind it. And then we have a cladding that sheds water and drainage can occur in between. This is essentially what we're doing with our joint. So we're not creating perfect barrier joints, we're creating what we call a two-stage seal, creating a drained joint system. And actually this is sort of normal too. So mass joints work the same way a mass wall works. They can get wet and there's nothing really moisture sensitive there. They just dry to the inside, but they're big, right? It's like a bedded joint. A perfect barrier joint needs to be perfect forever. And if it's exposed to UV, it needs a lot of maintenance. You know, buildings that are built this way, we constantly have to reseal them when that outer seal deteriorates because it's the only one. Now there's some options to kind of hiding these joints and protecting them, but anyway, you get the concept. A two-stage or drain joint is something that we see a lot in precast panels, for example, where we have, and it's what we do at windows. So we've got an interior joint that sometimes is installed from the interior, sometimes it's installed from the exterior, and it's completely continuous. And then we have this outer joint that's installed always from the exterior, and it has openings in it for drainage. And this one is the one that gets serviced or maintained. But what's great about it is this will last practically forever because it never sees UV, doesn't see any damage. This one gets can be maintained. We can replace this joint and it's accessible. It's easy for us to replace that joint without making our building unoccupiable for a period. It's not like replacing a roof where like you better hope it doesn't rain while you're replacing it. A lot of air traffic control towers are built this way, or hospitals with precast panels. Anyway, but this is the concept. Like these are the same, these concepts, or this concept of a drained assembly should be very familiar because it's here. It's what we're used to doing conceptually. So when we talk about real windows, we want to know this stuff first. We want to know whether or not the window has a flange, and if so, what kind of flange is it? Is it an integral flange or a snap-in flange? And I'll show you how to look for that. How the window is structurally supported. I'll also show you how to look for that. There's only a few options. And then we want to know the water and air control strategy for the wall. Is it a mass wall, a drained wall, or a perfect barrier wall? Those are just less common. And if it's a drained wall, what kind of WRB is used? What is the material in the adjacent wall that we're using to control water? And then the fourth thing, this ends up often being the trickiest, is where do we actually want to put the window in its sort of front back orientation within the opening. So these are pretty knowable things. You can figure this out. These are not that hard, but you'll want to know these things before you start detailing your windows. So, oops. So this is a profile for a window, an integral flange type window. These are really popular on sort of lower end or mid-range residential projects and multifamily projects. So these are vinyl window frames, and the flange is part of the same extrusion as the window. So there's no joint here. It's one monolithic piece. So you can see that here. There's a joint here at the mitered corner, right, where that the jamb extrusion meets the head extrusion or sill. But it's one monolithic piece. So that makes sense, right? You can see that these are the same part. Don't pay attention, by the way. This is what trips people up. You don't need to really concern yourself for like why this is open and this is like it doesn't matter. Look for whether or not there's a flange and look at how it's attached to the rest of the frame. That's going to be the sort of most relevant for you as you detail. But don't get tripped up on what this looks like for anything other than aesthetics for now. I mean, whatever, if your job is specifically, I don't know if you're a facade engineer, you have to care, but not if you're an architect detailing windows for the most part. So this kind of window is mechanically fastened to the structure through the flanges and through the sheathing right into the studs, right into the framing. Same thing if this were a metal stud. This is how it's structurally supported. And you'll notice that the flange ends up kind of dictating where the window is aligned in that front back orientation. This is the most common alignment for windows, and it's because they have a flange. So the flange will sit roughly flush with the exterior sheathing. So that front back alignment is basically determined for us if we're using these standard window types. This is a flanged window. You can see what it looks like. You see that flange there, and you can see the pre-drilled holes for where we're going to fasten it into the structure. Some more, you can see the flanges. And here's one when it's partially installed. Sometimes they break off a little bit. This is the other kind of flanged window. This is a snap-in flanged window. This is more common residentially. And I've never seen a snap-in flanged window on a multifamily project. This is mostly single family type work. And so I've got the profile here, and you can see that there's a joint there, right? You can see that this is a different piece than this, and you can see there's a receiver, because it's so the frame will be notched to receive this flange. Sometimes they come attached to the window and they're stapled to the frame, and that's how they're shipped to the site. And other times they're separate, and you'll have to the contractor, the glazing contractor, will actually snap them in later. And you'll notice, so you notice this joint here, and you can notice that it's pretty flimsy, right? That's not nearly as solid as what we saw before. What's kind of crazy is that really is how we fasten these windows to the structure. Now, this window will bear like gravity. It'll bear on the shims. I'm going to talk about that later, but it'll bear on the sill. So there'll be the load, the gravity load on the framing there. But the only mechanical attachment to the structure is through this flimsy little flange, which is kind of shocking to me, but that's how they do it. So it's fastened basically the same way. And you'll notice the alignment again is dictated by where the flange is.
Hey, we have a couple questions.
Go for it.
I think it was maybe from 2 slides ago, but how would you do the flashing for a box frame window? And the second is, what if the water buildup inside of an integral frame, or builds up inside of the integral frame through vapor migration? So
it won't probably do it from vapor, but we're going to talk about each of those as we go on. You guys are smart. You're thinking ahead, but we're not there yet. But we'll get there. Good questions. So this is another integral flange, and you can see the joint there, right, where the frame is. This is on a door. So it's, obviously partially installed. Windows can also be structurally supported with clips. So this is called clips, even though it's kind of a tab. I suppose you could call it a tab also. And it's fastened to the window here, and it'll get fastened into the jamb through this. Show you what that looks like. The drawing. This is a different kind of, or actually this is a similar clip. It's a Z clip. It'll have a Z bend in it. So this gets fastened onto the window before they put it in the opening. And then once it's held in the opening, then they'll put a fastener here. And it's the same attachment on the head and the jambs and the sill. I hate these. I hate these too. These are L. I don't like installing windows like this. A lot of high-end residential does this, which is, I just really don't like. So this is an L-shaped clip, and it can be installed entirely after the window is set, right? Because you have access to it. So usually they'll install at least one side first, usually the window. And then they'll fasten it into the framing. So this is a large Z clip on a commercial window. So you can see there's part of it, and then the other part you can't see. You'll have to imagine it on the jamb there and on the head. This is also a Z clip. This one's in bad condition because this is a leaking window. And this is so they come in pretty, there's a wide range of sizes. This is a pretty small one on a residential project. This is a pretty big one on a hospital.
One more question.
This is a medium-sized one.
I think you may have said it briefly. Someone said, can you speak on why you don't like?
Yes. I will tell you why, because I'm going to show you what I like better. I like this better. Now this is a commercial example, but don't pay attention too much to what the frame actually looks like. What I want to show you is how the frame, and this is a commercial job, so they've got concrete and they've got what's called an embed, a steel embed, which is essentially they put it in the concrete because they know they want to put a window here and they're going to attach it. But it doesn't really matter. It could be anything. This could be wood. This could be, don't pay attention to that part yet. What I want you to notice is that the fastener goes just perpendicular to the frame right into the framing, right into the structure. And it's located between our two seals. Like our seals aren't shown yet. I'm not showing you the detailing here, but our outer seal would be here and our inner seal would be here. And this goes right between them. It doesn't interrupt them. Whereas this makes it real hard to get our interior seal installed. Same thing with this. It interrupts things. Now, the great news for you guys to know that I am going to tell you that I hope you all remember and take this to your firms is when you spec a window that looks like this, almost all of the time, the manufacturer can do something like this. You just have to ask. Now, it's not always true, but more than half of the time it is true, where they can say, oh, you don't want clips? You want to just fasten right through the jamb or the frame? Yeah, we could do that. But you just have to ask. And it greatly simplifies detailing for you and in the field. We're going to talk about what that actually is going to look like later, but you can ask for a different structural system. You can't always do it for, the big commercial systems. Those are pre-engineered and you don't have as much play there. But for a lot of the residential, particularly high-end residential, there are options for how these things get actually attached. You can also ask them, this is not the case for this one, but on some of the very custom jobs, you can ask them to install a flange when there isn't a flange. Now, you might not want a flange. You might want an unflanged window, which we're going to talk about too, but you can ask them to do it and they'll weld it on some of these high-end jobs. So you have more, I guess, you have more leeway than you might know about. So this is a commercial system and it's going to get fastened right through the frame. Just trying to show you the orientation. On the inside, you can see they have these cutouts to allow someone to actually get the drill through there to install the fasteners. This is a wood framed opening, and this is what's called a shim. Now, this is a horseshoe shim for obvious reasons, and it's made out of plastic. Sometimes shims are made out of wood. I tend not to like those as much because wood shims are moisture sensitive, right? Plastic ones are not, although I don't get too uptight about what the shim looks like. The purpose of the shim is not really water management. The purpose of the shim is that our framing is never perfect. And we want our windows to actually sit level and plumb and look right within the opening. And so our framing won't be perfect, but we want our window to be perfect. So we'll use shims, and this is actually two shims stacked on top of each other. They come in different thicknesses, and you'll have, actually I have a bunch of them in that drawer behind me. And you'll just stack them however you want them to make up the difference in the wonky framing. The second benefit of shims for us, for detailing, is that they give us our little chamber, right? And they make it so that our perimeter seals, we have enough room for our perimeter seals. Our sealant joints are much, much better when we're not trying to seal things that are really close together, but not quite close together. We want a space of at least 1/4 of an inch to be able to seal them properly. Now, if we want a space that's 1/4 of an inch when we're actually doing it in the field, what do we want to ask for? You can this will be a little quiz for yourself privately, pop quiz. If you want in the field, your installer to have a minimum 1/4 inch sealant joint around your window, does that mean you should design the joint to be larger in your drawings or smaller? Decide for yourself. Here's some think time. Think. Okay, you want it larger. There's tolerances, things aren't going to be, if you want a minimum joint of a 1/4 inch, you're going to want to ask for probably 5/8 of a joint, 5/8 of an inch. Well, that's actually kind of big. maybe 3/8 of an inch is what you might ask. So there's some play there. Everybody has different different preferences, but you don't want it to be any less than 1/4 of an inch. Now, sometimes this happens, and you'll end up with joints that are too small. Don't stress too much about that, but 1/4 of an inch is about the minimum size of joint that we can really detail properly. And that's like here. I'll show you some pictures of that. Okay, so here's our shim. Here's our opening, and this is really a lot like this. So we've got self-adhered membrane. That's self-adhered membrane on our opening, and it's protecting our opening. And then we've got our interior seal here. Our window system is on the shim, and we've got incidental water can drain out from behind that flange. So we're going to look at some typical configurations and kind of reiterate these concepts, and you'll see sort of step by step how they work. And the first one we're going to start with is a flanged window with a fluid membrane WRB. Now we're starting, this is not the most common, but we're going to start here, and actually we're going to skip number 2 because it's so similar to the first one. But this is the easiest place conceptually to understand how to detail windows. Almost everything is a variation on this. But then we're going to talk about mechanically attached WRBs because that's the more common case. So pay attention to this one, and then you'll see how it's different when the WRB is mechanically attached. So we've got a flanged window. I'm going to pick that typical residential flanged window. It's got the snap-in flange. So you can see that sort of snap in there. And we're going to put it in a rough opening. By the way, that term is rough opening when it's a wood framed building. It's called a masonry opening when it's a masonry building. I called it a rough opening, or I used to call it a rough opening regardless of the opening type, and people are very upset if you use the wrong terminology. So now you know. Probably you already know. Anyway, so we know we're going to end up with something like this. We're going to have some sort of interior trim, some sort of window frame, some kind of cladding, and some kind of WRB. That's sort of the general gist. But we're going to start with this. So we just have our opening, right? So here's our framing at the head, framing at the sill, our exterior sheathing. We've got some insulation in here. That's all we've got. So the first thing we're going to do is we're going to add a wood nailer as a back dam. We're going to talk about this. This is going to help us create that chamber at the sill. And it's also going to make it easier for us to install that inner sealant joint at the sill. So we've got our wood nailer first, and then we're going to take the fluid membrane WRB, the same that's on the wall, and all we're going to do is extend it inward at the opening. We're doing that at the head, at the jambs, and at the sill. Just bring it right in. So just paint it in. Then we're going to set the window on a shim, and we can call this a membrane wrapped rough opening. So we've wrapped the rough opening with membrane, and we just set the window on a shim as necessary. Then we put our full perimeter backer rod and sealant joint on the inside, here and here, and we apply fluid onto the flange and onto the frame. And we want to be careful that we cover that joint, that snap-in part of the joint, extending the fluid right onto the frame. We do that at the head and the jambs, which I'm not showing you, but it's the same detail as the head, but we do not seal the flange at the sill. The reason we don't do that is because we want to create that chamber, and we want drainage and drawing to occur. We also don't know entirely how this window system works, right? And so we can have this approach will tolerate leaks in our window. Our window can be a little bit defective either now or sometime over the next 50 years that this window might be in our building. And it's okay. If it leaks a little, we've protected our opening and it drains out. This is awesome. This is such a forgiving system. It's really beautiful. So here we're done. We're dried in. Our window is set. But this doesn't give us enough information, right? We still have to install our cladding, and we still want to make things aesthetically work, but we're dried in at this point. From a water management detail, we're done. So this is actually pretty easy, right? This stuff is easy. What's hard is going to be figuring out what we want our trim to look like at the window and how that gets supported and all kinds of other stuff. But the window part itself is fairly easy. So let's assume we've got a panel cladding or something. What we're going to do is we're going to provide a secondary rigid head flashing. And the terminology there is important. It's a secondary flashing in that it's a rigid piece of metal that gets installed after we're dried in. So this is not helping us with waterproofing, it's water shedding. And it's reducing the load, the water load on our window. It's reducing how much water our window sees, which is good practice, right? It's sort of like you've got a raincoat on and now you have an umbrella. The umbrella doesn't, it doesn't do the job of the raincoat, but it reduces how much work if your raincoat has a hole in it and you have your umbrella on, it's less likely to matter very much. So it's another piece of metal, and we just have a second layer of fluid or self-adhered membrane that goes over it. Now this looks like a lot of buildup here. I'm going to show you a photo of what that looks like. I'm exaggerating the lines to make them more clear to show you, but in reality, these things look painted on. They look pretty monolithic. This looks very smooth when you see it. And I'll show you a picture. And then we have our cladding. This flashing serves as a termination for our cladding too. Sometimes our cladding will have a different termination or some other piece like that. But this is the general concept. Now this would work. It's important to note that this would work without the secondary flashing. We could just install the cladding by itself. Sometimes the secondary flashing gets value engineered out of the project. I don't like doing that because windows are so high risk. It's such a no-brainer way of reducing risk, and it's just a piece of bent metal. How hard, like why VE it out? But you don't always get your way, right?
There's a question.
Oh, sure. Oh.
Sorry, I'm getting a call.
No problem.
Is there another layer of ROF fluid applied below and on top of the metal flashing?
Yes, it's another layer. So you've got one layer, the first pink line I'm showing bright pink for anything flexible and sticky. So you've got a bright pink line that goes into the rough opening. Your second pink line goes over the window flange and onto the frame of the window to dry it in, and then you're done. And then the third pink line is a third coat that goes over the top leg of this secondary flashing, the water shedding piece. It's very important not to seal underneath that, right? Because if this isn't perfect, we get a little water here, we want that to drain. It's almost always more important to provide drainage than it is to, and let gravity be your friend, than it is to attempt to block water. You're not going to be good at blocking water. You will never be perfect at it. So best to provide drainage. It is okay to seal here, right? Though, because this is a different scenario in terms of what gravity is happening. So if this seal isn't perfect, or if any other seal isn't perfect, it's fine because we still have drainage, safe drainage into the cavity behind our cladding, where our rain screen, our drained assembly is still working exactly the way it's meant to work. Do we have another one, Tyler?
Yeah, one just came. If you have a leak in the header, is the culprit that peel and stick most often? Sometimes not. I mean, we're kind of, we're good at, we have a diversity of ways that we screw this up. I'll put it that way. Sometimes it is that. Sometimes it's just a lot of times it's the window system itself. Sometimes it's the window to wall interface, like that if we're not using, the fluid flashings are awesome, especially the acrylics, at really staying bonded to the substrate there. But some self-adhered membranes will peel away. We call it fish mouthing. And that can happen over time and create a leak. Yeah. But again, we can tolerate a bit of a leak. Our opening is protected and it drains out at the bottom. That is what makes this so awesome, is that this approach means we can tolerate imperfections in what we've bought and in what we've installed.
And a lot of times I get, and we're going to get to this more later, I get, well, if your window's leaking, you have bigger problems, which I really hate that line of argument. It's sort of like just throwing your hands up and saying like, I'm no longer going to have this conversation, which is annoying. Like, let's actually talk about it. And that's not true that you have bigger problems. Maybe you do, I don't know. Maybe we shouldn't do anything. I have like 100% of the problems I have in my life are more important than any given window. Does that mean I shouldn't do my job? Anyway, the whole point of this is to create something that's forgiving and tolerant. And windows see a lot of abuse. First of all, they have a lot of internal joinery that makes them very hard to design to be watertight in the first place. And then they're manufactured and loaded and packaged and put on trucks or ships or whatever, and they're jostled around, they get installed. These things see a lot of abuse before they even end up on the building. And I think it's really an unrealistic expectation to presume that they're going to be perfect, even on day one, never mind on day 10,000. We expect windows to last a long time. Why don't we design them so that they have a prayer of actually lasting a long time? Especially since we can. This is, anyway, I hope I'm preaching to the choir here. But oh, okay, one more question, go for it. Oh.
Would the bottom seal at the sill not?
I'll read it.
I know this question. I'm gonna
not have weeps. Here we go.
I know the question. I'm gonna answer it. I'm gonna answer it in a minute. But the short answer is we really want to drain this, even on the coast. Now, I'd like to point out though that this is what's called a concealed weep. Right? This isn't exposed. We have, I mean, it's not directly exposed. This is relatively protected. If there were ever a safe place to provide a drain, it's right here. It is almost always better to, I mean, almost always, it is better to drain this in almost any configuration. Now there's one exception to this in commercial construction that I will talk about later, but in 99% of the applications, we want to provide drainage in this location because we are not perfect anywhere else. Our materials aren't perfect, our installation isn't perfect, and this is what allows us to not be perfect. We don't have to be perfect. Drainage is not a bad thing. Like I said, these seals work together. This is water shedding, this is waterproofing. It's a two-stage approach. And I think we've really got to get it out of our head that this is a backup if we've screwed up here. That is not how this works. These work together. This doesn't, we do this on purpose so that we can tolerate this very thing. And it's what makes it durable. So some frequently we ask questions up to this point. We've answered some of them, but is it okay if instead of a wood nailer, I slope the sill? Isn't it important to slope the sill? Why don't I show that? Yes, it is important to slope or you can, all things being equal, it'd be great to slope the sill. So sloping the sill means this: you can cut this wood frame here or wood framing member to give a slope to the sill instead of adding this wood nailer. So that's the question. And you could do either one. You could do either, or you could do both. In most commercial construction or multifamily residential, I find it's easier to do the nailer because the nailer gets installed by the glazing contractor. The same guy that installs the window installs the nailer. I find it difficult in commercial construction. It's not always true in residential construction to get the framing contractor to slope the sill. He doesn't like to do that work sometimes. Sometimes you get him to do it. The trickiness too with sloping the sill is they don't always cut the existing framing to achieve the slope. They'll take a piece of clapboard siding, which is sort of, triangular in profile, and they'll lay it down here, which is a great way of creating a slope. But what does it do? You can think privately, quiz time. If I put a triangular piece of wood here, what effect does that have on the rest of my system? It means that I've just made my rough opening smaller. So if I'm going to have enough room for my perimeter seals, I need to order smaller windows, or I need the framing to be bigger to accommodate that. I might be getting real tight if that's how I achieve my slope. Now, if you've planned for this, if you've got a contractor who's planned to do this and has sized the windows accordingly and done the framing accordingly, that's fine. But I find doing the nailer like removes that question and we don't end up arguing later. It's personal preference. Most residential contractors in sort of the building science world will show us a sloped sill. In commercial construction, we see this. All things being equal, the slope is nice, right? Because gravity acts down. But what works here is that if I get some incidental water here, and I will, if it's only a little bit of water, or if it's a substantial amount of water, it'll drain anyway, right? Enough water, it'll drain. It's not going to go inside because I've got my back dam. It'll drain out. If it's only a little bit of water, my opening is protected and it'll just evaporate. So how much bigger should my roof opening be than my window? We talked about this, but you should accommodate at least, at a very minimum, you want that perimeter seal to be 1/4 inch. So you're going to want to design the sealant space, the perimeter space, to be larger. So 3/8 of an inch on all 4 sides is pretty nice. Can I use foam for the interior seal instead of backer rod and sealant? Absolutely. People often prefer to use foam. It's sort of standard, particularly in cold climates. Isn't insulation really important? It is, except it's so small that the difference in performance that you would see from using foam instead of backer rod and sealant is really pretty small. If you use spray insulation to achieve that inner seal, you'll want to use backer rod anyway, like maybe you install your backer rod here. And the reason for that is you don't want to fill our chamber. You don't want to completely fill that with foam because you want to preserve the ability for the system to drain. So foam is fine. Foam is very common in single family residential. I don't like it that much, honestly, because it's hard to tell if the foam is really continuous, but I defer to whatever contractor I'm working with, whatever their preference is, we can work with that. Do I really have to drain the sill? Isn't taping the sill flange better for air control? What if I'm in a coastal environment? What if I'm using high quality European windows? We talked about this before. No, you still want to drain it. I can't stress this enough. You still want this system to drain. It's very, very, very important. You will not be perfect. Your windows will not be perfect. Your contractor will not be perfect. And even if they're perfect today, they're not going to be perfect in 10 years, in 5 years, in 10 years, in 20 years, in 30 years, in 50 years. These windows see a lot of abuse. There's a lot of moving parts. Design some forgiveness into the system. I think I talked about these things. We're gonna skip to, because we're getting kind of over on time. I want to show you one more residential window, and we can talk about commercial windows another time, I guess. I get pretty excited. Oh, I wanted to show you what this looks like to use a fluid membrane to seal this stuff up. So I showed those lines kind of separate, but look how nice that is. So we've got an integral. This is the fluid membrane is pre-applied to the sheathing in the factory, and then we're using a fluid membrane for detailing. And this is over the flange of a window. So this line shows the flange of the window. And then this sort of indentation is from when the first layer went in, and this is the third. But notice how smooth that is. It's really kind of nice. But if we want to look at, this is what the inner seal looks like. This is what the flange at the sill looks like. So this is not sealed and this is sealed. So they've put the fluid over the flange, and you can see the indentation from the nail. You can see the nail here. It's a similar thing, but we're not sealing it here. We're going to let this drain. This, do you know what this is? Quiz for people. This is a little weep for the window system itself. So all that stuff I was talking about, how window systems are designed, this thing is designed to weep, and this will be exposed. So if window manufacturers design their own systems this way, it's a pretty good indication that we can design the window wall-to-wall interface the same way. But let me show you, this is the secondary head flashing, and see how it's taped. It's taped at the sill. This is a no me gusta. Not good. I don't like that one. Okay, so this last one, because you're going to see it so much, we're going to spend 5 minutes and then we're going to go to questions. And I'm sorry I'm so late. But Michael told me we could go late, so blame him.
It's no problem.
Okay.
We're happy to have you.
Good. All right. Okay, so here's a flanged window with the integral flange, and we're going to want to put it in an opening, but instead of having a fluid membrane as our detail membrane or our adjacent WRB, we're going to use a mechanically attached membrane like Tyvek or Typar or Dow Weathermate Plus. And those are very, very common on a lot of residential jobs and also multifamily jobs. Very, very common system. And what's kind of interesting is that because they are so common, we kind of base a lot of our understanding on how windows are supposed to be detailed on those systems, even though they're sort of, I think they're kind of, that this approach is going away. We're going to start using more and more fluid and integral membranes in the future, but a lot of what we know about window detailing are assumptions based on this. So we're going to put a different kind, the integral flange, and we're going to put it in our same rough opening, but with a mechanically attached WRB. So the most important thing to know about mechanically attached membranes is that they are, in fact, mechanically attached. So this means that they are not fully bonded to the sheathing behind them, and that water and air can and do get behind them. Not a lot of water, not a lot of air, but a little bit. And of course, water is going to be most significant for us when we're detailing windows, but this is how water gets behind. We staple these things up onto our sheathing. So of course, a little bit of water gets behind them. It's okay. We can work with this. We just have to know that it is occurring. This is only one kind of penetration, right? We also, after this happens, we mechanically fasten our cladding through our WRB into our framing, through our sheathing into our framing. So we've got thousands of penetrations through our mechanically attached water and air control membrane. So what that means is that at the head, we always want to seal the window flange to the sheathing itself, not to the mechanically attached membrane. And practically speaking, this means that we cut the membrane at the head. We do sort of a diagonal cut on both sides. You can see this here. And then we temporarily tack up the WRB so that we can detail our window. And then we'll flap it back down later, but we temporarily tack it up. My alarm here. We temporarily tack it up so that we can detail the window first. I'm going to show you what that looks like, but this is what it looks like at that stage. So in section, we've got our same opening, we've got our WRB, and we cut it and we tack it up, put some tape on it to roll it up and expose the sheathing. At our sill, we install our wood nailer just like we did before. And then we're going to take self-adhered membrane and we're going to install it over our mechanically attached membrane. So we've cut the mechanically attached membrane roughly flush with the sill. Sometimes they do it about an inch down, but whatever, roughly flush. And then we have our self-adhered membrane that goes like this. Now, what do we do with the jambs? There are two approaches at the jambs: the standard approach and the lower risk approach. This is when you're talking about Tyvek, which is the most common one. Tyvek accepts both of these, but for a long time they actually didn't accept this. They started with this, and this one is lower risk but more costly. So they would pick this, right, because it makes them more competitive with other systems. But anyway, I'm going to show you both. They're pretty similar. But in one approach, we take our mechanically attached membrane and we roll it right in to the opening. So the mechanically attached membrane is the dashed line. We roll it in. That's jam option A. And then the lower risk option is to cut our mechanically attached membrane about an inch from our opening and to take self-adhered membrane and bring the self-adhered membrane in. So this is what jam option A looks like. We take the membrane and we just roll it in. Pretty standard. And then this is what option B looks like. We cut, this is a mock-up. We cut the Tyvek, and then we use self-adhered membrane, and we put it at the sill and at the jambs. Closer view. So here's our back dam. This is the stretchy membrane to conform to these corners and stuff, and then self-adhered membrane into the jam. Okay. So back to our section here and our stages. So we've got our tacked up thing, we've got our protected sill, and then we've done one of those two things at the jambs. We didn't do anything at the head. Notice that. We didn't do anything at the head except expose the sheathing. So we set our window on a shim or a couple shims, a shim pack. And then we actually do this last, we provide our interior seal, usually last, but anyway, for the purposes of our conversation, we can talk about it first. And then we put self-adhered membrane over our flange at the head and the jambs, but not the sill, because we want drainage to occur from behind that flange. At the jambs, it looks just like it did before, but now we have self-adhered membrane. So both is the same. We back bed the window. I don't have time to talk about why we do this, but just notice that they don't actually have to do this anymore, but they do. Or they don't have to do it with other window systems, but the window manufacturer requires back bedding the flange and sealant. You want to do it at the jambs and the head, but don't let them do it at the sill. Why not? Because we want drainage. And they'll place the window in the opening. Notice that it's tacked up. It's got the sheathing has like a white kind of paint on it. I think this was a requirement for, it's like a mildewcide or something like that. It doesn't always have that. This was a requirement of whatever local municipality it was. So you see it going in there. Closer view. And you can see the sealant that's sort of smooshed out from behind the jam. Then they put self-adhered membrane over it. You can see they put it at the jam first, right? Which is good practice, because ideally you want everything to be shingle lapped. And then they're putting self-adhered membrane at the head. And then we do same thing as we did before. We put our secondary head flashing with another piece of sticky stuff. And then we lap the mechanically attached membrane down over everything, but we do not seal it. Don't seal it. Why? Because water gets behind the mechanically attached membrane. You want to drain it out. Now, sometimes manufacturers will tell you to tape it. The reason they tell you to tape it is because, I don't know why they do this, but Tyvek markets itself as an air barrier as well as a water control layer. And when they market something as an air barrier, they want to make it airtight. Well, it's not a terribly good air barrier to begin with because of stuff like this. You always want to prioritize water management over air management. And whenever we're using a mechanically attached membrane, our de facto air control layer is our sheathing anyway. But you do not want to tape it. You want to permit drainage at the head. Otherwise, you risk making your window leak. When it's finished, it looks like this on the interior. So here's our full perimeter interior backer rod and sealant. You can see how the interior joint lines up with at the sill and the jam, right? It's continuous. And this is we call it our membrane sill flashing. This is that wood nailer. And here's the membrane jam flashing. Flashing, by the way, doesn't have to be rigid. So I say membrane to indicate that it's flexible. Most of the time flashing is a membrane. It's not metal, it's not rigid. And I think that is pretty much it for the major stuff. I will say maybe we have 30 more seconds to tell you about. No, let's not confuse it. We'll start with we'll leave the most common systems. I can unmute. There we go. If we want to maybe have a different, I'm going to invite myself back, Michael. If we want to do commercial window systems another time, we can.
Absolutely.
We can do that.
Absolutely. As often as you want to come, we'll have you.
But I should tell you that with commercial systems, the approach is the same. It is the same. There's one exception that we detail curtain wall systems differently, but architectural windows and storefront systems, the principles are exactly the same. It's a two-stage seal. So the question I get asked most often is, how many sealant joints do I need when I'm detailing a window? You need at least 2. You often actually have 4, because in addition to these 2, you're going to have, I showed it in a framed wall here. Let's show something finished. What's finished? Okay, so in addition to this one, this seal, which is with tape, not with with a Beckerud sealant joint. In a commercial system, it's not flanged, so you'll have this will be Beckerud sealant. But anyway, so you'll have this seal, you'll have this seal. You might, in a commercial system, have an additional seal somewhere out here as a cladding closure seal, not at the head, but you will at the jambs and probably the sill. And you'll likely have another interior seal, because I'm not showing any trim here, right? So once trim gets installed, you might have a sealant joint there. So you might end up with 4. A lot of times we end up with 3 sealant joints in window systems, but 2 are the ones that are sort of tied to the window system itself. So you'll have 2 seals that are installed by the glazing contractor, and then an additional seal might be installed by the cladding contractor as a cladding closure seal, and then the 4th might be installed by an interior finish contractor as part of the interior finish system. But anyway, the concept for commercial and residential, it's the same. It is this 2-stage approach.
Christine doesn't know this, but I'm going to send her an email with some kind of a regular thing where she comes back every.
I would love that. This is fun. I'm also
X
an
months or
Amber
something.
book. Michael said that he was taking my course. I'm taking his course. So I'm going through the Amber book with you guys also. Anyway, well, so, but I broke the rule, right? I guess we can do it here of telling, I broke Michael's cardinal rule of
What's my rule?
don't tell people you're taking the Aries.
Oh, right.